Okay, everyone, you may have an idea what we need to do with the problems, right? Let us correct it together. You can keep the papers yourself so that you can review it later. But after class, please take a picture of that and upload it to Moodles, which I will count for your class participation. Okay? For the people on Zoom, unless you have a problem with your health. Okay? Now let us do it here. This is a polynomial. Can you see it clearly? Okay, very good. The first question is, what are the real zeros? This is another name of the solution, right? We call it real zeros. It means that when we need to find the value of x such that, let me write it here. Okay, let me copy it here. Such that f of x is equal to 0. Okay. At which value of x, f of x is 0. Okay, now let us do it. The equation is x cubed minus 3x. We need to solve fx equal to 0, right? That is to answer the question. And the function f of x, it means that x cubed minus 3x. We need to solve this equation, okay? And it's even better when we're given that x, take one, that paper, yeah, thank you, yes, each of you takes one. Okay, I'm sorry about that. Thank you. So now, or in this forms, we are given a better forms, x minus square root of 3 times x plus square root of 3, right? We need to solve for this. So it means that which value of x give us this equation? What is the solution of this? Yes, the first one is x is equal to 0, or x is square root of 3, or x is negative square root of 3, right? There are three solutions. Okay? And here, you can see it on the graph here. The three solutions. This is negative square root of 3. This is 0, and this is square root of 3, right? We can see it immediately on the graph. So determine the multiplicities of the real 0, or determine the multiplicities of the solutions, real solution. I remind you to review in this Math 1021, but you may not. So let us review what is multiplicity of an equation. Okay. So the definition of this is, suppose C is a real 0 of a polynomial function of f of x of multiplicity k, that is x minus c to the k, is a scalar, is a factor of the function f of x, then the shape of the graph of f of x near c is as follow. So the first case, if k is larger than 1 and k is an even number, okay, then the graph of f of x near c will be somehow like this. It will touch the x-axis at c. Or another situation is that it will touch the graph at this point. Okay? And another case, if k is larger than 1 and k is an odd number, or k is odd, then the graph will cross the OX axis at the point C. It will be somehow like this. Or it's crossed like this. Okay? These properties is very useful. So, okay, this is the main things. X minus c to the k, then k will be the multiplicity of that 0. Okay? In our case, now let us look at the equation, the function f of x here. So what is the multiplicity of x when x is equal to 0? Very good. At x is equal to 0, then the multiplicity of that is 1. Why? Because here, you can look at this. It is x to the 1, right? At 0. And here, similarly, it is x minus square root of 3 to the 1. And the same is like this guy, right? So similarly, what is the multiplicity at x is equal to negative square root of 3? What is it? Very good. And the same story with x plus, take one paper. Yes. Very good. Yes. And at x is square root of 3, then multiplicity of this 0. Yes. Okay, very good. So we see that all these solutions, they have the multiplicity is 1, which means that 1 is an odd number, right? Then near 1, near this solution, the graph should cross the x-intercept, right? And x-axis. Or you can see it here in the graph. Let me copy it. And place it here. Oops, oh, stupid. Or you can look at this, okay? These are the solution, and the multiplicity of them is 1. Therefore, they cross the x-axis at the solution. This is at the solution negative square root of 3. This is the solution x is equal to 0. And this is square root of 3. Is it clear? Do you see that properties now? Make sure that you see it. So the multiplicity, let us write it here. So the solution, let me use a different color. It's 1 right here, right? And the same story. Therefore, they cross. Okay. And does it make sense? Okay. And find the critical numbers of f of x. And if you don't remember, look at the definition of critical numbers. It is where the first derivative of the function is equal to 0 or it does not exist. So in order to find these critical points, what should we do? Yes. Look at this. Thank you, Daniel. So here, this is a polynomial of degree 3. Therefore, it is continuous with all x in R, right? And it is polynomial is also differentiable on its domain. Therefore, the f prime is always exist. Let us take it. Okay, now in the question 1b, let us find f prime of x. Okay, and we know that f prime of x, which is the derivative of x cubed minus 3x prime, right? And what is it? Very good. It is 3x squared minus 3. Okay. This is the derivative for any point in the domain. So
even if it gives us a graph, we want us to use the derivative to find the zeros?
yes, if you are given the graph, definitely you can look at that graph and determine it, right? But in order to find the correct number, sometimes you may not see, yeah, the graph may not be that beautiful. And this is the general way to find it. Find the derivative and set that to be 0 so that we can solve for critical points, okay? So now we need to solve f prime is equal to 0, or in this case, it will be 3x squared minus 3 equal to 0, right? So how can we solve it? Yes, you add 3 both sides. Therefore, we have, very good. And then, yes, 3 minus 3 divided by 3, which is 1, right? Therefore, x will be, very good. So there are 2 points satisfying this condition. So therefore, we found 2 critical points, right? So let us say, let me just write them separately. Or x is -1. So this is the first critical point. This is the second critical point. Okay. Is there any other way to find the solution without doing this way? From the graph is one way, right? Or look at this. If instead of solving this solution this way, I can do it this way. Here, 3 is a common factor, right? So let us factor 3 out. It is 3x squared minus 1 to be 0, right? Okay. And can we factor it, write it differently? Yes. It means that this guy should be 0 and this guy, or this guy should be 0, and we find the same things, right? So anyway, it's okay. Now, so we found 2 critical points. Let us look at that on the graph. At x is equal to -1, it is this point, right? Okay, and look at this. What is the derivative, the slope of this guy at this point? Yeah, the slope of this is like this, okay? Makes sense, okay? How about at 1? This is another critical point, right? And the slope of that point is also very good. So, makes sense. We found 2 critical points. And by looking at the graph, is it a maximum or minimum here? Yes, local maximum, right? Or just write it max here. How about this guy? Yes, local mean. Okay. That is. So this is also the global max, it is not a global max because you see that at this position, this is f of -1, which is 2, right? But we see that on the right of this, there's always value larger than 2. Yeah, it's just going on. There's no global maximums here. Okay, just review it in the book, just reread it to double check it. But now these are all important things we need to care in section 4.1, right? So today we will study, one more thing. What is the question C? Okay, show all the rows 0 on the graph. We have already done, right? Very good. So let us continue the section 4.2. So in this section, we will study the mean value theorem. Before doing that, let us study the Rowe's theorem. So given f is a function f of x, if f of x is a continuous function on a closed interval from a to b, and the second condition, if f is differentiable on the open interval a, b, and the third condition, if fa equal to fb, then we have there exists a number c in the interval a and b such that f prime at c is equal to 0. So this is the Rowe's theorem. We have three conditions, then we have this conclusion. Okay? So this is the Rowe's theorem. Let us take a look at this graph. The first one. Okay? The interval we consider here is from, let us say, from 1 to 3. In our case, a is 1 and b is 3, right? And the function f here is a constant, is flat here. So first, is it continuous? Yes, it is continuous, right? You can draw it without taking the pen up. So 2, it is differentiable, right? The constant differentiable, because derivative of that gives us 0, right? It is a special case of a polynomial. Okay? Therefore, the second condition is satisfied. And the third one, f at 1 and f at 2, suppose this is 2. So we see that f of 1 is 2, f at b is 2. Then it satisfies all three conditions here. So what does it mean? Therefore, it satisfies all the hypotheses of the Rowe's theorem. We conclude that, okay, there exists a number c in this domain. Or in this case, the number c would be any number between 1 and 3, right? And we see that the derivative of that are 0, is 0. Slope is 0. Is it clear? Do you have any question? Okay, just apply the theorem, right? And another situation. If the graph is like this, here, x here, okay, y, and in general we call it a and b, right? Okay, fa and fb are equal to each other. So first, this function is continuous on the closed interval from a to b. Okay. The second condition, is it differentiable? It is a quadratic function, right? Quadratic function is differentiable on continuous and differentiable on R. Therefore, it is continuous from this interval. Third, fa and fb, are they equal to each other? Yes, they're the same value right here. So therefore, we can apply the Rolle's theorem. It means that there exists a number c somewhere between a and b, and the slope of c should be 0. In this case, the point C is this point. Okay? Then, how about this guy? Okay? The function f of x here is given as this. And the point A and B now are 2 and 7. First, is it continuous? Yes. And it is a polynomial, right? So it is a polynomial and continuous and differentiable in these intervals. And we see that f at 2 equals f at 7, which is 2 in this case. So therefore, it's satisfying 3 hypotheses of the Rolle's theorem. We say that, okay, there exists a number c such that the slope of c is equal to 0. In this case, how many points satisfying that slope? Yeah, there are 2 points. The first one is somewhere right here, let us say 3.5, right? Here is, let us call 6 right here, okay? So we see that these 2 points has 0 slope, okay? Very good. And it may look like this, x and y here. If this is A and this is B, let us write it A and B in general here. And FA and FB are equal to each other, the same story. They are continuous, differentiable. And FA is equal to FB, so there exists a number C between this interval such that the slope of that is 0, okay? That is the Rolle's theorem. Okay, now let us study this example. First, prove that the equation x cubed plus x plus 1 is equal to 0 has exactly one real root. Interesting. So, what do we need to prove here? There are two things we need to prove, right? First, it has a solution, a root. And second, the root is unique, right? We need to prove. And we need to prove okay, we need to prove two things. So when we prove the exist real root, which theorem do you think about? We have studied together, and there is one theorem that proves okay, there exists a solution in some intervals. Do you remember? The intermediate value theorem, right? Yeah. So we need from this. So it reminds us about the intermediate value. And second, we need to prove it is unique. Okay. So how can we do that? Okay, let me remind you about the intermediate value theorem. Okay, on an interval A to B. So it says that if it is continuous from A to B, right, then if FA is different from FB, there exists a number between A and B. Okay, okay. In our case, A and B here, let us consider the interval from 0 and 1. We see that, okay. What is f of 0? Yes, it will be 0 cubed plus 0 plus 1, which is 1. Did I type the wrong? This is negative 1. sorry, this is -1. So it means that f at 0 here will be -1. Second, let us take a look at the number 1. So what is the value of the function f at 1? Yes, 1, be careful, because we changed the sign here. So it is 1. So look at this. We don't know the graph of this function yet, but we know that at 0 it is -1, somewhere here, right? And at 1 it is 1. Oh, let me pick it better. This is -1, this is 1. Okay, we know that the function f here at 0 is -1 and at 1 is 1. And the function here is a polynomial of degree 3, right? It will be continuous in R, or it means it will be somehow like this, right? When x goes to -infinity, it becomes a very small number, so it's below here. When x is very large, it will go up here. Okay, that is somehow like this. So, and we see one more thing. We know the two values, right? And furthermore, f0 is not equal to f1. Okay, and f of x is a polynomial. Therefore, it is continuous on its domain. Right? Therefore, it is continuous on 0, 1. So it's satisfying the intermediate value theorem. So what do we have? So there exists, for any value c, so there exists between fa and fb, which mean between -1 and 1 here. It means that there exists a c in 0, 1 such that fc will be 0, right? So from this, we can conclude that, okay, this function has a solution, for sure, from intermediate value theorem. Okay. And the second thing we need to prove is that it has exact one solution. Okay. So okay, we know that it has a solution. And the second things we need to prove that we need to prove the uniqueness. So now we prove by contradiction. suppose that so we suppose that there is another real root let us call it FA and FB, right? The first solution is A, the second solution is B. Okay? Now we need to find something wrong. Okay? Okay? If there's a solution, then FA should be equal to FB and equal to 0. So the function f is continuous. It is differentiable from A to B, from all over the domain. And now the two values, A and B, are equal to each other, okay? Therefore, we can apply the Rolle's theorem. Okay? First, we see that it is continuous and differentiable on A and B. And from A, FA is equal to FB, so we can use the Rolle's theorem. What does it tell us? The Rolle's theorems tell us that there exists a number C in the interval A and B, right? Such that F prime at C will be 0. That is from Rolle's theorem. Okay? So, but we have that F prime of X will be the derivative of X cubed plus X minus 1, right? Derivative, which will be yes, 3x squared plus 1. Okay? So x squared, how does it, is it larger or smaller than 0? Any number square will be larger or equal to 0, right? Therefore, how about 3x squared? still larger than 0, right? Then we see this is f prime, right? How about 3x squared plus 1? How does it look like? How does it compare? Always larger than 1, right? So from this, we see that this guy is always larger than 1. Therefore, fc, f prime of c will be always larger than 1. It cannot be equal to 0 here, right? We cannot find any c in A to B such that f prime of c will be 0. So this is the contradiction. Therefore, there's only one solution of this equation. The solution is unique. Or there exactly only one solution, okay? And let us see each other tomorrow. Thank you.